Last but not least, we have the hyperbolic paraboloid, which is the most complex of our quadric surfaces. The good news is that we're not going to do all that much with this surface in this class. You are responsible for knowing how to identify it. I'm not going to require you to try to draw it ever. We will revisit this quadric surface when we're talking about certain calculus concepts, which is why we're going to go ahead and show it anyway. It is very useful for certain examples. Now, to explain what's going on with a hyperbolic paraboloid, first of all, we know that it is a paraboloid because of the fact that we have a non-squared variable. So that is the key here. We've got one variable that is not squared. Now, the way we know that it's hyperbolic is because the signs on my squared terms are opposite one another. So that is key. That's the distinction between an elliptic paraboloid and a hyperbolic paraboloid. We know that ellipses, as two-dimensional curves, require both squared variables to have the same sign. And hyperbolas always have opposite sign. So that's how you know the difference between whether or not it's going to be an elliptic paraboloid or a hyperbolic paraboloid. It's whether or not the signs of the square terms are opposite. So the hyperbolic paraboloid kind of looks like a saddle, which is why you see in my key features and talking about a person and a horse. You can imagine that I have some person riding a horse right here, for example, and my horse is like over here. He's like, "Hi, I'm a horse," and there's a saddle on him, so his butt's over here. Okay, so anyway, we're going to take a look at how this works. So per usual, we're going to look at our traces. And so when we look at the xy plane, in this case, that's when z is 0. If I set z equal to 0 in my equation, I end up with this equation here. Now, because this is kind of similar to what happened when we looked at elliptic cones, we have opposite signed squared terms equal to 0, which allows us to solve for one of those variables in terms of the other. That produces lines. Now, I have not drawn those lines in my picture, but I could add them to my graph. They would look something like this. Here is one of those lines in the xy plane. And then here is another one of those lines. The lines aren't super helpful for figuring out how to draw this, so that's why I sort of left them off my initial picture. If I go and I look at z equals c instead, so I'm going to bump my z value up, and so I'm going to be looking at the height of z equals c. You'll see in my picture that I have what look like hyperbolas. This is why it's getting that hyperbolic paraboloid name. When I look at z equals c, if I look at what actually happens with the algebra, when I plug in c for z, this left-hand term becomes 1. And then I'm just left with a standard equation of a hyperbola, and because it is y is positive, this is opening in the y direction. Now it's opening in the y direction at the values y equals plus and minus b. If I wanted to visualize that on my graph, I could think of this as coming down here. This is like y equals b. And here, this is negative b. It's just that the vertex is shifted up to the value z equals c because that's where I'm looking. Now, if I were to look at z equals negative c instead, then my left-hand side of the equation would become negative 1. And if I put that in standard form, it would be that the x squared term is now our positive term. And so I am going to get hyperbolas that are opening on my x-axis this time. Oh, and I noticed I didn't even write hyperbolas up here. So this is hyperbolas on the y. And then in this case, I get hyperbolas on x. And so looking at my picture, hyperbolas on x, that's what this is here. And that's what this hyperbola is here. And this is down at negative c. And so you could think of, if you want, you could think of this location here as being x. This location is like positive a. And then it's tough to see back here, so I'm not going to try to draw it, but where your other hyperbola is opening, its vertex is at negative a. Now, when I look at the YZ plane, this is when x is 0, and when x is 0, this squared term goes away, and I'm left with something that when I rearrange is a parabola equation, because I have my non-squared variable on one side equal to something squared. So the sign of this coefficient is going to determine whether or not I'm opening up or opening down. Now, the way I have drawn my picture assumes, so my graph assumes that c is greater than 0. If c is greater than 0, then I end up with a parabola that is opening up in the y direction, which is why this parabola is up. And if you look at the xz plane, you also get a parabola, and its coefficient, again, which direction it's opening, is based on c, and that's why this would be opening, sorry, I'm missing a negative sign. That's why this would be opening down. Either way, you need to know whether or not c is positive or negative in order to know that you have which direction your parabolas are opening. So both of these are a parabola. If you always are careful to arrange your equation such that when you put, so notice I've put a note here, when you arrange so that the non-squared term is positive, so basically you put the non-squared term on one side, and then you make sure that when you put it on one side, that is a positive value, and then you write out what these terms are. So if you always assume that the coefficient associated with z is going to be written in such a way that it will be positive, then you'll be able to say that this parabola will be up when c is greater than 0. Now it would flip and become down if c was less than 0. It just has to do with how you arrange your equation. So it is important, if you want to make sure you know who's playing the role of the horse is generated based on whose parabola is up. So horse equals the up parabola. And if you don't want to, if you get confused about how to determine by memory, what you can do is you can just say, hey, kill off one of the squared variables by setting it equal to 0. Write out the equation of the trace. Is your parabola up? If it's up, then that's your horse axis. If it's down, then that is not your horse axis. So in this case, the way I've drawn my picture, because I've assumed that c is positive, I get a parabola down when c is greater than 0. The key important features here is to figure out which axis your parabola is opening up. That will be your horse. Your non-squared variable is going to be the axis where a person would be sitting if they are riding that saddle or riding the horse in the saddle. That's it.